Cool. Well, let's get rolling. Just in case, I'm gonna take off the mute for now. Module number 6, blink twice, and we're almost done with the course. We have software assurance best practices as the main topic of today. The majority of this I have seen in interviews. So if I was you, I would pay particular attention, not to the lecture, because with the lectures, I'm going over things, but really the labs, the work that you'll be doing this week, I would highly suggest that you spend time understanding as you're doing, reading all the material that is provided, doing the labs, understanding what it is, because I've seen this stuff show up over and over in interviews. So first off is the software development life cycle. The SDLC maps software creation from an idea to the end of software's useful life. Software development doesn't always follow a formal model, but most cover these phases. SDLC provides a consistent framework to structure workflow and provide planning for the development process. Each SDLC model has certain types of work and projects that fit better than others, so simply picking an SDLC model may not always be the best choice. In this one, there is the planning feasibility, the initial investigation, whether the effort should occur, look into alternate solutions and high-level costs for each solution. Then we have analysis and requirements. Customer input is sought to determine desired functionality, the current system application does or doesn't do, desired improvements. In the design phase, we have designing for functionality, the architecture, integration points and techniques, data flows, business processes, etc. There's coding, where the actual coding happens after all that design and talk and storyboarding. Then comes testing, formal testing with the customers or the dev team. Units or software components are tested to ensure proper functionality, as well as connections to the outside services, data sources, and other integration. User acceptance testing occurs to ensure the users are satisfied. Then there's training and transitioning, ensuring end users are trained on the software and it has entered into general use. This phase is also called acceptance, installation, and deployment. There's the ongoing operations and maintenance, including patching, updating, minor modifications, other work, and then end of life. When the software is no longer used, it's outdated, and time to get replaced by something new. Question for you, where's security? Testing, design, testing, I see. By default, testing is nowhere. It should be everywhere. Yeah, typical, right? Yes, this is how software ends up with bugs, ends up with extra things that malicious folks find and use to exploit, because security is not part of this cycle. And you're right that it should be everywhere, but it's not. So you have to find ways to integrate yourself as the security professional into this process without slowing it down. Because that's the thing that developers hate. They hate to get slowed down. So something that you have to think about that I have seen questions of is not necessarily in the test, but in interviews, in the technical interview, how do you handle that? How do you handle working with a dev team who has their schedule, who has their deadlines, and you find bugs that need to get fixed before it goes out? Because losing money and damaging the reputation of the company is pretty big versus fixing something before it goes into production, right? Like the risk is very different. Yet dev teams don't quite like to work with us because we slow them down. So something to think about as you think about getting into the field is, how do you inject yourself into this process without slowing it down? The SLDC, just the process itself, does show up in Security Plus in the test. So does this guy, the Waterfall, a software development model that's not necessarily used as much. This is a sequential model where each phase is followed by the next. Phases don't overlap, and each logically leads to the next. Waterfall has been replaced in many organizations because it's seen as relatively inflexible. It is a fixed, well-known, but it's not quite the one that's used. There's Spiral, uses 4 phases that are repeatedly visited. It provides greater flexibility to handle changes in requirements, as well as external influences such as availability of customer feedback and development staff. Spiral provides the possibility for rework or identifying design requirements later in the process that require significant design change due to more requirements coming to light. I ask you again, where does security fit? Right, it should be everywhere. But do you see it here? Not so much. The one that I do see a lot of companies using is Agile. And mind you, for these processes, you don't have to know them in depth. You just have to know about them. So Agile is an iterative and incremental process rooted in 4 basic premises. Individuals and interactions are more important than processes and tools. Working software is preferable to comprehensive documentation, which I laugh. Customer collaboration replaces contract negotiation. Responding to change is key rather than following a plan. Agile breaks work into smaller units to be done quickly with less upfront planning. Focus on adapting to needs rather than predicting them, with milestones identified early but subject to change. And yet again, security is not here. You have your work cut out for you. DevOps, development operations, combines software development and IT operations with the goal of optimizing the SDLC, using tool chains to improve those elements of the SLDC. DevSecOps describes security as part of the DevOps model, as a shared responsibility part of the entire cycle, integrating security into all the work done to produce application and services. The role of security practitioners in DevSecOps includes threat analysis and communications, planning, testing, providing feedback, and ongoing improvement and awareness responsibilities. But you also have to think about the other folks, the development folks, and their frustration with us sitting at the table. To them, we're just another roadblock. And we have to work with that. We have to understand that. We have to work with that to help them see that having us on the team at the table is a good thing for everyone. CI/CD, continuous integration and continuous development. CI is a development practice that checks code into a shared repository on a consistent ongoing basis, from a few times a day to automatic check-ins and builds. The main goal is enabling the use of automation and scripting to implement automatic course of actions that result in continuous delivery of code. Using CI/CD requires building continuous validation and automated security testing into the process, finding new vulnerabilities and fixing them before an attacker or any rogue developer inserts flaws that are deployed. The Open Web Application Security Project, or OWASP, has a list of proactive controls for securing coding practices. This list is from 2018. It's for security techniques that should be included in every software development project. Now, of course, we say should because they're not always implemented, but you have a place of reference when you have these talks with developers in language that they understand. Let's not forget APIs, application programming interfaces. Those need security as well. APIs are interfaces between clients and servers or applications and operating systems that define how the client should ask for information from the server and how the server will respond. Programs written in any language can implement the API and make requests, making them tremendously useful for building interfaces between systems or a point of vulnerability. API security relies on authentication, authorization, proper data scoping, rate limiting, input filtering, and appropriate monitoring and logging in order to remain secure. Okay, questions so far? There's still more to cover, but I feel like that was a lot. All of that, in a way to try to sum it up, is people who code suck because they just focus on coding and don't think about security. Go figure, they're not paid for that. That wasn't the profession. They just learned to make programs and not really think about security. It's on us to gently, in a professional manner, inject ourselves into that conversation, into that table, to ensure that what's being made, what's being written is secure. Knowing that we're going to have pushback, knowing that it's an uphill battle. So we have to learn how they think. We have to learn of these processes because we have to inject ourselves into them without throwing everybody off and causing more mayhem. I have 2 more sections on code, and then we're moving on. There are a couple of code review models that you should be familiar with. Again, you don't have to be the expert in them. You don't have to be the Agile expert or the Waterfall expert. You just need to know about them because they do show up on the test. There's pair programming, Agile development technique, placing 2 developers at one workstation. One writes code while the other reviews it. There's over the shoulder. That's again a pair of developers. The writing developer explains the code to the other, allows for peer review of code and assisted understanding how the code works. There's pass around code review, manual peer review done by sending completed code for reviewers to check for issues. This is where documentation will be more important. And then there's the tool assisted that relies on formal or informal software-based tools to conduct the code review. There's also this thing called the Fagan inspection, a structured formal code review intended to find a variety of problems during the development process. It specifies entry and exit criteria for processes, ensuring that a process is not started before appropriate diligence has been performed. Now, if only that diligence was also security and wasn't just code. The last section of code before we move on to the second half is analyzing and testing it. Static code analysis is reviewing the source code for an application without running the program. This can be done using automated tools or manually reading it. Dynamic code analysis relies on execution of the code while providing it with input to test the software and can be manually done or automated. Fuzzing involves sending invalid or random data to an application to test its ability to handle unexpected data. The application is monitored for crashes, for failures, or incorrect responses. Fuzzing identifies simple problems and not complex logic or business process issues. Questions on that first half before we move on to the next half, and or give you a moment to breathe and scream at a pillow, because that was a lot. And there's more to go. I am not a fan of coding. So that part of the security plus test, I always have the hardest part getting through because I understand it the least. Not even gonna lie. I get it, but at the same time, like, have us at the table. We're here for a reason. In fact, it's not our fault that you wrote bad code. We're just trying to help. Okay. So this second half, is and isn't outdated. So this second half relies around the OWASP top 10 vulnerabilities. It's really an introduction into that. As usual, Industry moves forward, and academia is behind the curve. So the next couple of slides has information in this order, in the 2017 order. This was recently released, where things have changed or merged. So for example, in 2017, the top vulnerability that existed on websites was injection. And that has fallen to third. Broken access control is now the #1 vulnerability in websites and web services. So as I'm going to go through this list, understand that the top 10 is this list here, the 2021. The topics that we're going to cover are still here. You still see things like cross-site scripting. You'll still see like SQL injection. You'll still see them. They're just not in the same order of criticality. Does that make sense? Because I don't want you to memorize outdated content. That's one of the blessings and curses of security, is things change really quick. Okay. #1, again, because it was #1 in 2017 up to 2021. The first item that I'll talk about is SQL injection. If you have no knowledge of SQL, I have a site in the lecture notes that'll help you grasp an understanding of how SQL works. It's called SQL Bolt. It is an online interactive exercise site, so you don't have to install a database server or do anything of that. They already have it on their site that you can use to learn SQL. Now, SQL injection, or as we say it in the industry, SQLI. Web applications often receive input from users to compose a database query that provides results that are returned to the user. For example, if a user enters orange tiger pillow into a search box, the web server needs to know what products in that catalog might match the search item, sending a request to the backend database server like the following: retrieving a list of items that can be included in the results. Looking for an item name, item description, item price from products where that item name could have things like orange, tiger, and pillow. A SQLI attack may send unusual looking requests, like these three. The little apostrophe up here, a double dash. If the web server passes this request along to the database server, it would look something like this. Different from the first. If the command is successful, it would run 2 SQL queries separated by the semicolon. The first would retrieve the product information, the orange tiger pillow. The second would give us a list of customers and their credit card numbers. There's the blind SQLI. In this attack, the perpetrator sends input to a web app to see if it's interpreting injected code before attempting to carry out an attack. For example, a web application is asking for an account number. When a user enters an account number on the page, they'll see a list of information associated with that account. And our underlying SQL query could look something like this. The $sign account field is populated from the input field from this box right here. An attacker can test for a standard SQLI vulnerability by placing outputs such as a little apostrophe or 1 = 1: ; This query would match all results because 1 does equal 1. SQL does math. This query would match all results. However, the design of the web app may ignore any queries beyond the first row. If so, it would display the same results as earlier. Though the attacker may not be able to see the results of the query, it doesn't mean the attack was unsuccessful. Receiving no results makes it difficult to initially distinguish between a well-defended application or a successful attack. The attacker could simply try again with a known account number and using SQL that modifies the query to return no results, like this. The query will not return results because 1 is never equal to 2. The application returns nothing. If the application returns nothing, they can be reasonably sure the application is vulnerable to blind SQLI and will attempt more queries to alter the contents of the database or perform other unwanted actions. There's also the blind timing-based SQLI. These attacks depend on delay mechanisms provided by different database platforms. For example, Microsoft has a function that waits 15 seconds before performing the next. An attacker seeking to verify whether an app is vulnerable to a time-based attack might provide something like this. An application that immediately returns results is not vulnerable to timing-based attacks. Though it may seem strange, a strange form of attack, it does extract useful information. If a database table contains unencrypted fields, named passwords, for example, an attacker could use this to discover passwords by checking letter by letter. There's command injection. In some cases, web apps may execute a command within the operating system. This is dangerous as the attacker can exploit a flaw and directly manipulate the OS. If a web app used for classes made directories within the operating system, an attacker could add that to a string and cause the OS to make a directory and delete itself in the OS. Or other more nefarious things. Passwords used to be the most common form of authentication, the most easily defeated because they're knowledge-based. An attacker who learns a user's password may impersonate the user until either that password is expired or changed. Passwords can be learned through technical manners like wiretapping, password dumps, brute force, through social engineering, through fake websites, through spam. Developers make it easy sometimes by shipping systems with default passwords. And the user or the administrator also makes it easy by not changing that default password. There are section attacks. Session attacks. Credential stealing attacks allow a hacker to authenticate directly to a service using a stolen account. Session hijacking takes a different approach by stealing an existing authentication session. They don't require the attacker to gain access to the authentication mechanism. Instead, they take over an already authenticated session with a website. Most sites use cookies, which are saved in the browser and transmitted as part of the HTTP header. The cookie is a storage object that holds variables that may be later accessed by a website who created them. If an attacker is able to steal a cookie, they can impersonate that user to the website that issued it. Cookies can be stolen through wiretapping on unencrypted network connections, installing malware on the user's browser, engaging in man-in-the-middle attacks, and other ways. Once the attacker has the cookie, they can alter it and access the site themselves, and that's called session replay. Web developers can protect against cookie theft by marking cookies with secure attributes, which prevents cookies from being transmitted over unencrypted HTTP communications. For Windows, there's NTLM pass the hash, just another way of stealing Windows passwords with the same exact premise. We have unvalidated redirects. Some web apps allow the browser to pass destination URLs to the application and then redirect the user to that URL at the completion of the transaction. In this example, the web app would send the user to the thank you page at the conclusion of the transaction. While this can be convenient for developers to modify the destination page without altering the code itself, it does create an unvalidated redirect situation where the attacker may redirect the user to, you guessed it, a malicious site. We have insecure direct object references. In some cases, web developers make an app that directly retrieves information from a database based on an argument provided by the user in a query string or a post request. There's nothing wrong with this approach as long as the application applies other authorization mechanisms, as the attacker can view the URL and modify it to retrieve other documents. If there is no authorization check, then it'll be easy to view other information that exceeds their authority. We have directory traversal. Some web servers have a misconfiguration that allows users to navigate the directory structure and access files. These directory traversal attacks work when web servers allow the inclusion of operators that navigate directory paths and file system access controls don't properly restrict the files that are stored elsewhere. So in this example of going to mycompany.com, if it allows us to add this, then we are able to get to the Etsy shadow file on that server and be able to read it, extract that information, go crack passwords, and now we have our way in. There's file inclusion. File inclusion executes code contained within a file, allowing the attacker to fool the web server into executing arbitrary code, either locally, if the file is already on the web server, or remotely by having a file downloaded and then executed. Usually, attackers exploit this to get a web shell to then issue more commands and view the results in the browser. This attack can be done both HTTP or HTTPS. And attackers could seek to repair the initial vulnerability and prevent other attackers or security team from being notified of the successful attack. Because that's not enough, we have more to go. Cross-site scripting. Cross-site scripting occurs when web apps allow an attacker to perform HTML injection on a web page. Here we have reflected cross-site scripting. These attacks commonly occur when an app allows a reflected input like hello name. An attacker can utilize the script tags used to embed scripts in web pages to trick the browser into doing something it shouldn't on the web page. For example, if the following text is entered into a web app that says like Mike script, and it says hello, the browser would process it and display a pop-up saying hello rather than displaying the page in the page itself. This can be used to run malicious code that asks for passwords and transmit to a third party. The key to cross-site scripting is it's possible to embed form input in a link. An attacker can create a web page that loads a real web page, but executes the script included in the input by the malicious user, which appears as part of the valid web page. Developers should perform input validation on their site. They should have applications that determine the type of input the application will allow and validate the input to ensure that it matches a pattern. For example, if a text box allows a user to enter their age, it should only accept 1, 2, 3 digits as the input. Everything else should be rejected. There's the stored or persistent cross-site scripting. This attack stores cross-site scripting code on a remote web server. So it could be done like that to add more to it. An attacker could insert HTML script code, causing future visitors of the site to see the message. But I mean, in this case, it's just a little alert thing that pops up, but it's easy enough to do worse things. Something like this. Cross-site request forgery is similar to XSRF, but attack the trust that remote sites have in the user system to execute commands on the user's behalf. XSRF attacks work by the assumption that users are often logged into many different websites at the same time. Attackers will embed code in one site that sends commands to a second site. When the user clicks on the link to the first site, they unknowingly launch a command to the second. Developers should protect their web apps against XSRF by using secure tokens that the attacker would not know to embed in links. Check the referring URL in requests from the end users and accept only those that originate from their site. There's also server-side request forgery. This attack tricks a server into visiting a URL based on user-supplied input. SSRF attacks are possible when web applications accept URLs from a user as input and retrieves information from that URL. If a server has access to non-public URLs, SSRF attack can unintentionally disclose information to attackers. So some application security controls that we can implement to fight against these things and more for web apps is input validation, where we have what is allowed to be inputted versus what is not. For example, that the prior one of, if we have a box where a user types in their age, it should not accept anything other than a 1 to 3 digit answer. Any other character should not be allowed. There's web application firewalls that work at the application layer, sit in front of a web server, receive all network traffic heading to it, and scrutinize the input with validation. For databases, we need to use things like normalization. It's a design principle to prevent data inconsistency, prevent any update anomalies, and reduce the need for restructuring. Parameterized queries, where the client doesn't send SQL code directly to the database server, they're inserted into a precompiled query template. So there is already something pending. When a user submits something, that doesn't go directly to the database. We're just going to put it into a template and then on its way. Under obfuscation and camouflage, we have things like data minimization. Don't collect sensitive information that you don't need. There's tokenization, replacing personal identifiers with unique strings in the lookup table. And hashing, replacing sensitive information with irreversible or alternative identifiers. If you add salting to those values with a random number, it'll make them even more resistant to attacks. Under code security, we have code signing, confirming the authenticity of developers' code to the end user. We have code reuse. Security professionals should be familiar with the various ways that third-party code is used in their organization, as well as the ways that their organization makes services available to others. It's fairly common for flaws to arise in shared code, making it important to know what dependencies exist and remain vigilant about the code base. There is software diversity. Watch for places in the organization that are dependent on a single piece of source code, binary executable files or compilers. Tracking them is a critical part of securing that code base. Code repository. Have centralized locations for the storage and management of application source code. Code repos perform version control and handle dead code, things that are no longer used. Insecure coding practices. We have comments. Developers should ensure that commented versions of their code remain secret. Compile code automatically removes any comments from executable files. Web apps that expose their code may allow remote users to view those comments. There's error handling. Attackers thrive on exploiting errors in code. Developers must anticipate unexpected situations and write code that steps in and handles errors in a secure fashion. There's always hard-coded credentials where developers include username and passwords in the source code. This is a form of a backdoor, like keeping API keys in a GitHub repository that an attacker can easily use to get in. Lastly, we have memory management. Number one, resource exhaustion. Intentional or accidental. Systems may consume all memory, storage, processing time, and render the system disabled or crippled. Memory leaks is one example of this. We have pointer dereferencing. Memory pointers are an area of memory that store an address on another location. Attackers can use null pointers, where the pointer is empty, to cause an app to crash, giving debugging information that's useful for reconnaissance and to bypass security controls. Buffer overflows, where an attacker manipulates a program into placing more data into an area of memory that is allocated for that program's use. The goal is to overwrite other information in memory that may be executed by a different process running on that system. There is the race condition, otherwise known as talk to, time of check, time of use. This occurs when a program checks access permissions too far in advance of a resource request. Developers should evaluate access permissions at the time of each request rather than caching a listing of permissions. We have unprotected APIs that can lead to unauthorized use of functions like modification of services. If it's not meant for public use, don't let it be accessible to the public. And driver manipulation. Device drivers do have low-level access to operating system and run with administrative privileges. It's perfectly possible for an attacker to install a malicious driver and refactor it so that it rebuilds with the original source code and these new elements. Questions on this wealth of information? Like I said, that second half was more tied to 2017's top 10. You really should know the 2021. In either case, you have quite the labs in front of you for this week. You're going to go to two main sites. The first one is called Application Security. They have an awesome walkthrough where you don't have to install anything. It's all in the browser, but it gives you a run through of some of the things we discussed and more. So you get to see in a nice sandboxed environment how these attacks work. All that you're doing is submitting proof that you completed going through these items. They should not take you that long because it is a walkthrough and it does tell you what to type, what to cut and paste, what to notice. So it's not meant to be the biggest part of your work this week. The biggest part will be going to the Web Security Academy. They have an awesome array of labs that go far in depth, that give you the chance to be on the driver's seat and do the labs, do the things that we talked about, like blind SQLI, like cross-site scripting. You will be doing them. Web Security Academy is free, and so is their main tool, Burp Suite. So you can download and install that, can make an account on Web Security Academy and go crazy on their various labs. For example, cross-site scripting has 30 labs to do. CSRF has 5. XSE has 9. Do them. Learn and understand how these attacks work by doing them yourself. As always, you are more than welcome to work together. If you get stuck, there is a walkthrough. They do have answers, and that's okay. I will tell you, I am not the biggest fan of web app security. It's not really my cup of tea. So I understand those of you who will go through this and go, this is not my thing. You can look at the walkthrough to help you get through the assignment. The biggest thing that I want you to do understand is how these attacks work, how to describe them, how to talk about them, because those things do show up in interviews. You don't have to be the expert. You just have to understand what they are, understand what they're saying, and be able to use your words to describe them. Does that make sense? Or did I confuse you even more? Cool. Well, as usual, we'll get to work.